I think I wanted to bring about ideas in a sort of like growing level of complexity, and also more or less in historical order.
There is a car whose engine is completely backed by hydrogen fuel. So is it kind of okay to presume that it might be a future?
If I have a battery, what a battery is a machine that converts chemical energy into electrical energy. Okay? And the total energy is the same now as it was 7 billion years ago.
Hello everyone, I welcome you all to a mindful conversation with Dr. Theo. He's an astrophysicist whose research includes dark matter exploration, guys. And not only that, he's also into galaxy formation. And now he's bringing his expertise into the world of higher education. Welcome, sir.
Hi, thank you.
Okay, so before I get any deeper into the conversation, there's something I'd like to ask you. The conversation we were having off the camera, you mentioned that this course is designed in a way that it's good for non-specialized students. So when you say that, can I assume that this course is structured in a way that it can be accessible by everyone who is not into physics and maths?
Yeah, so the idea is that I've always felt there was a bit of a gap in what's available to people who are interested in physics, in that you have either pop science books, which are very accessible but fairly non-rigorous, and which I think have value as they're engaging, they're entertaining, and they're a good way to bring people to kind of like be interested in physics as a subject. But their lack of rigor means that they're not very useful as ways to really teach the concepts that underlie the realm of physics. And then on the other end of the spectrum, you have sort of specialist physics courses, which are obviously highly rigorous and the way to actually train a physicist. But they come with a heavy mathematical burden.
Yeah.
So ultimately, if you want to practice physics, there's no getting away from it. You need the mathematics, and it's the only way to do it rigorously. But I would argue that today more than ever, there's a need to have an ability to kind of understand scientific concepts and be able to engage with them in a way that is intellectually rigorous, without necessarily having the means to apply them as a specialist would, but just have a broad but serious understanding of the concepts, and so in the course this year, one of the concepts that I keep coming back to is, for instance, energy, which is perhaps one of the most ubiquitous concepts in our media and cultural environment, and which has come to mean pretty much anything. It's we use energy colloquially to mean everything from vibes to actual electrical energy, and I think it's interesting to give people a sort of like a rigorous introduction to how that concept came to be, how it's applied within the field of physics, and how it's also abused in pseudoscientific fields.
Well, going through the entire description of the course, there are 2-3 things that hit me the most. Okay. You have mentioned about the ideas of symmetry, irreversibility. So can you put some light on it? Like, what inspired you to go through those ideas?
Yeah, so basically, I think more or less as an aesthetic choice, I wanted the course to be a 3-part thing. Okay, so just something about it appeals to our sense of aesthetics. But more seriously, basically the first, I think I wanted to bring about ideas in a sort of like growing level of complexity, and also more or less in historical order. So it turns out that historically, our notions of momentum and energy emerged before our concepts of entropy and irreversibility, and then the notion of complexity as we currently understand it, that would be second half of the 20th century. So basically, the idea was that concepts of symmetry in physics have a very central role. So basically, what we mean by symmetry in physics is not exactly what is meant in sort of common usage. What we mean is that there are certain laws of physics which do not change depending, for instance, on where in space you are, on whether this whole system is rotated, and whether it's translated through space or through time. And these symmetries have something to do with what's known as conservation principles, which I think a lot of us have a sort of intuitive understanding of a few of these. For instance, we all know that energy is conserved. I think there's this somehow it's our common education has taught us, at least, that you can't create energy from nothing, but in the same way that you can't create matter from nothing. So these conservation principles, they emerge over the course, very slowly over the course of the 17th, 18th, and 19th century. and they come to be central planks of physics as a field. So I think I started with symmetry because the concept of symmetry encompasses all these conservation principles, so matter, energy, momentum as well.
Yeah.
And they're a good historical introduction, I think, to the field of physics, as well as being something that we can grasp intuitively. The second part was entropy and irreversibility, which are a slightly more subtle concept, which emerges in the sort of like latter half of the 19th century and become rigorously defined in the very late 19th, beginning of 20th century. This as a concept is really, to me, is perhaps one of the most interesting, because it's basically trying to answer the question, well, if the nature of physical law is that things are conserved and things don't change, so for instance, the total energy of the universe is conserved. If you think of the universe as an isolated system, then the total energy is the same now as it was 7 billion years ago. The total momentum of the system is the same now as it was 7 billion years ago. So this kind of begs the question, okay, so given that we observe that there is change, what drives the change? And the answer is that the fundamental laws of physics can tell you nothing about that, because they don't actually give you a direction for time. If you typically, an example that's often used is if you imagine a world without any kind of friction, without any heat dissipation, things like that, then a bouncing ball would just bounce up and down forever.
Yeah.
Okay. And the question is, why is this actually not the case? Why is it that we all know intuitively, if a film is played backwards, if a film of a bouncing ball is played backwards, we know full well that the version where the ball jumps up spontaneously is incorrect in a very fundamental way. And the notion of entropy is an attempt to gain a rigorous understanding of why it is that, despite the fact that the total energy of a system remains conserved, somehow there's one course of events that conserves energy but is pretty much physically impossible, namely the air molecules in the room bouncing against the ball and making it bounce up and down, and another course of event, which is the one we all observe to be the fact, which is that the bouncing ball loses its energy.
From your answer, I got 3 points. Complexity, symmetry, and irreversibility are the fundamental of these courses. But there's one more question I'd like to ask you. I come from a tech background. I come from a science background, physics and mathematics. But I've always been curious, how does it all make sense? Where does it come in the real world? So I'd like to ask you, sir, can you give me a real world example in which all of those are interconnected and doing an interplay?
Yeah, so I think perhaps the most kind of practical example of all this is when we think about energy, right? Because as we kind of all know now, there are different forms of energy which can be converted one into the other. So for instance, if I have a battery, what a battery is a machine that converts chemical energy into electrical energy. Okay. What the principle of conservation of energy tells you is that all forms of energy are sort of interconvertible in a fundamental sense. But then the interesting question arises, if it's so easy to convert one form of energy into the other, then why is it so difficult in practice to actually build batteries, to actually create forms of sustainable energy? If it really was that easy to just convert the energy of the sun into usable work, then we shouldn't have any problem doing this, right? And I think so. The example I give, the concrete example I give, is actually there's this big field in energy studies that has come up, which is the hydrogen economy, and in particular the notions of green hydrogen. Okay, so to sort of give context, one of the big problems that we have as a society, obviously, is that we rely on fossil fuels to do most of what we need to do. The great advantage of fossil fuels is they're very energy-dense sources of energy, meaning that a kilogram of coal, you burn it, and it will give you 30, 40 megajoules of energy, which is a lot. On the other hand, you would need many solar panels to generate the same power. So there are a whole bunch of applications where renewables can't really directly be used, right? So for instance, you can't use solar panels to run a car or an airplane. And so there was this big question, which was, okay, so we actually know other forms of fuels which do not emit any greenhouse gases. Namely, if you burn hydrogen reacts with the dioxygen of the air and just generates water molecules. So if we could somehow produce vast quantities of hydrogen, then we could fuel next generation airplanes, cars, etc. And the thing about hydrogen is that it's very easy to obtain, theoretically, in that if you take some water and you electrolyze it, meaning that you apply a potential difference that is sufficient to separate the hydrogen from the oxygen, then you can basically create infinite reserves of hydrogen from seawater. And then the question becomes, so why do we not do that? Because it turns out that to do this at scale is very difficult. And actually, most of the ways in which in the real world, the way in which we produce most of the hydrogen is not from water, but from natural gas. So not renewable, certainly not green. And so given that, if you look at the equations, right, which is that the chemical transformation is, hydrogen splits into oxygen and, water splits into hydrogen and oxygen. This is how you obtain the hydrogen. And then in the fuel tank, you just do the opposite. Okay, hydrogen and oxygen turn back into water. So given that this should be a perfect cycle, there should be no worry here. Energy is conserved. You put in energy to split the water molecule, and you get that energy back when you burn the hydrogen. Basically, what thermodynamics tell you is that because entropy must always increase, there's no way to do this cycle perfectly. Basically, you'll always be overall spending more energy. Okay, and in practice, what this translates as is that we do not have a green hydrogen economy. And I think some people are optimistic that one day we will, but not in the very near future. And I think people have been saying that we would get to a great green hydrogen economy for a very long time. And I think some of these claims are actually basically backed just by commercial interests, and that people who work in the field of green hydrogen have vested interest in saying that this is the future. And really, I think that conversation, that debate, really is something that you kind of need to have on the scale of society, and that people need to be well educated enough on the physics of it and the chemistry of it to be able to critically assess. Okay, what are the real issues here? Because again, on a surface level, this is a great idea. And it's just, but with a sort of like minimal understanding of the laws of thermodynamics, you immediately come to understand that the question is not as simple as it seems, and that really this is I've taken the example of hydrogen, but you could do that with pretty much any question surrounding the problems of energy and renewability, sustainability, etc.
Since you mentioned about hydrogen fuels, few days back I was seeing a reel on Instagram that there is a car whose engine is completely backed by hydrogen fuel. So is it kind of okay to presume that it might be a future?
Oh, so the thing is, hydrogen cars have existed for decades.
Yeah.
So that they tend not to work with hydrogen fuel directly. So basically, there are two ways to get energy from hydrogen. Either you burn it directly, so this is how rocket boosters work typically. So hydrogen reacts with liquid oxygen, explosion, rocket up. There's a second way to do it, which is not using hydrogen directly because it's highly explosive, where you basically store the hydrogen in a kind of battery, basically. And these are kinds of things that we use to power cars. So basically, these are known as fuel cells usually. Mm-hmm. The idea being that what you're building is a kind of hydrogen-powered battery. And indeed, this works. So we have had these kind of batteries for a very long time. It's just that they've been plagued by two big problems. The first one is the question of storage of hydrogen, because obviously hydrogen is a highly explosive gas, so you can't store it anywhere that is in contact with air. So there have been proposals for instance, kind of metallic materials that have the ability to fix the hydrogen and release it when necessary. So the storage problem is a big one. But the really, really big one is actually how do you produce the hydrogen? Because it's all well and good to have your car powered by hydrogen, but if you're producing the hydrogen by cracking methane molecules, then you're just displacing the problem. The other way of creating hydrogen is by doing electrolysis. So basically, you have a water molecule, you split it using electricity. So again, that's all well and good, but the question is, where does the energy for this come from? And then you have two options: either you've got a coal power plant or some other fossil fuel burning power plant that is emitting CO2. So maybe your hydrogen isn't emitting CO2, but the way you produced it is. So first one. And then you have when we talk about green hydrogen, what we mean is hydrogen that's produced using hydrolysis or electrolysis, and where the electrolysis is powered by renewable energy. So basically, the electricity that you use to split the water comes from solar or hydroelectric or some form of renewable energy. But then the problem is actually a little bit more subtle here. It's like, okay, if, as a country, you're spending, however many gigawatt hours to produce all the hydrogen fuel that you need to power your cars, you're not using that power to, heat people's homes or to, make the rest of your economy function. And so the question becomes, okay, so what uses are you displacing by using all this energy to create hydrogen fuel? And if the answer is that you've had to open a different coal mine and a new coal power plant in order to augment your electrical production capacity, then that's no good either, right? I think this is the kind of thing where I think it's good to reason kind of in terms of the physics of it, because you sort of I think once you see energy systems as being connected, once you kind of like have an intuitive grasp for how nothing is truly reversible, how there's no perfect recycling cycle, there's no free lunch basically when you're talking about energy. I think that gives you the intellectual tools to kind of like see through a lot of kind of like fluff, right? And that's again, there's a genre, I think, of media that is rampant, which is sort of like scientific infotainment, which I don't mean to criticize too harshly, because I enjoy YouTube videos about great engineering and stuff like that. But you always have to realize that ultimately the headline grabbing claim will more often than not be pretty misleading. And I think I've seen hundreds of videos claiming that great breakthroughs in green hydrogen. And all of them, it only takes, I think, a modicum of physics knowledge to realize that the claims are at the very least overblown. And I think basically having a solid, if non-mathematical understanding of what the laws of thermodynamics are, of what is energy, why the conversion from one form to another is never actually that obvious, that I think is a pretty key thing.
That's a really great answer, sir. It all makes a lot of sense now. One more thing I'd like to ask you, coming to you only, you have been a researcher for like very long time, and you're also getting into the education thing. So you have seen both the sides. So what's your take on that? Like, what all challenges you have faced in your entire journey?
Basically, so when I designed the course that I'm teaching now, actually, the question of how you teach physics was sort of like looming fairly large in my mind, because I've had the experience of teaching high school physics for a couple of years as well. So I've done sort of like every level, and I've always been interested by the difficulty in teaching high school level. In many ways, I've taught university tutorials and things like that. In many ways, it's far easier to teach at the university level, I found, despite the material itself is more challenging for the teacher and for the students. But somehow the students have already self-selected in a way, so that you're already talking to people who are who are intellectually familiar with the methods of physics and stuff like that. With high school physics, the interesting thing is that you're talking to an audience that doesn't really necessarily either care or understand the whole point of physics, and I think like the particular frame of mind, the way that a physicist approaches a problem or an idea, is actually quite odd. It's a difficult. It's filled with intellectual and epistemological obstacles that need to be overcome somehow. And I think that was one of the reasons why when designing the course, I decided I'd be talking quite a bit about history of science. Because in many ways, the history of science is a way to illustrate how these kind of intellectual and epistemological obstacles occurred and how they were overcome in the course of the development of physics as a field.
When we were having that conversation, you mentioned that you came to Alliance University before, right?
Yeah. So last year I was teaching a course with one of the three themes, basically, which was complexity and chaos. And the idea there was sort of, similar in terms of the goal. So teaching a sort of conceptually rigorous but non-mathematically intensive course for liberal arts students, so that they could familiarize themselves with concepts in physics. And I'd chosen complexity because so the sort of like anecdotal story is that I have increasingly had this frustration of the consensus on climate change, for instance, being challenged by people who are just saying, oh well, look at the weather, right? Or people conflating the difficulty that we have in predicting the weather next week with our baffling ability to predict whether climate system is going to be like in 100 years. And that's that apparent contradiction, I realized it speaks to a misunderstanding about the way that physical models function. Because ultimately, when we're talking about weather models, we're talking about very chaotic models, which intrinsically are not reliable beyond a few weeks. Whereas when we're talking about climate models, we're actually talking about models which have a very reliable and very well-established structure. And they only become difficult and unreliable when you're talking about very, very long durations or very large shifts in temperature. So that was the thing. Basically, I wanted to have a course where we look at physical models and try to think about what are the properties of these models? Are these linear models whose behavior is well understood, well defined, and which are kind of the usual models that we used in physics all the way up to the 19th, 20th century? Or is this model that we're using nonlinear? Is it going to be sensitive to initial conditions in a way that makes them, despite still being deterministic models, it makes their application difficult and the results sometimes unreliable?
Well, as we are at the ending of the episode, there's one question where I'll be summing up all the things. How is your overall experience at Alliance University? How do you like the infrastructure, students, and of course the food? We cannot leave that. And your entire experience in Bangalore.
So food was great. I've had a very good time for that. So Bangalore, I've not explored that much. I've stayed a lot on campus, which is very pleasant. I think the greenness of the campus is really lovely. And as far as the student experiences, it was interesting. So basically, I found sort of mixed responses, I think, to the course. Which I think is maybe also partly my fault. I think in a future course I might emphasize the history of science a little bit less and start with the concepts a bit earlier, maybe, because I was sort of experimenting with the balance to strike between these two things. As far as the students themselves, I found some have seriously engaged with the course, and I've been pleasantly, well, not surprised, but I've been struck by the fact that they seem to really engage with the material, that they have a reasonably good grasp of fairly complex concepts that have been introduced during the course. Then there's also, apart from that, the perennial disappointment with students who seem to have decided that ChatGPT was now their homework source. But I think that's kind of inevitable.
Yeah, well, that's a nice conversation, sir. I really loved my time with you.
It's been great. Yeah, thank you.
And I really hope we can shoot more episodes like that. Thank you so much, sir.
Thank you.
Yeah, thank you, sir.
Thanks a lot. Have a good day.